this? What is the dashed IS representation?
Down the curve line. That's not good.
Is it an equal to or is it a less than?
Oh, it's a less than.
It's a less than. What is the BS? It is an equal to. So everything that we have done the last couple of periods where we were talking about the surface, what were we talking about? We were talking about an equal to. The surface is equal to this, okay? So we had a bunch of points on the left, or we had an infinite number of points on the left, which represented points on the surface, okay? We had this definition on the right, which was mapping functions and blending functions and a few control points on the right, but it was equal to. Now what we want to do is we want to figure out, well, how does this work with our math? So before we get there, let's talk a little bit about Boolean operations. Okay. So the Boolean operations are unite, subtract, intersect. It's the common set of Boolean operations that you're taught in mathematics. Those things are the operators inside of our CAD systems. How do we get access to those? Well, in NX, if we're creating functions inside of NX, there's a little pull-down area where you can say, I want this subtracted, I want this added, I want this intersected. What happens with kind of Pro-E and CATIA? What's that?
Infers that you want.
It infers. It looks at that and says, I think I know what you want, and it doesn't. It doesn't ask you, do you want it intersected? It just will unite or it will subtract. It does the operation that it thinks you want. Can you override that inside of CATIA or Pro-E?
Yeah.
Absolutely. There is the tools pull down area, and in that area, you have the standard Boolean operations that you can force it to do something different than what the inference engine actually allows. So here's the mathematics of solids, and it's a bit of an eye chart, but it's taken straight out of your book. So if you look in there, you're going to see a column for IS, and what is IS? It's the inside, so what do you expect the math operator to be down here? It's going to be less than or greater than, depending on which way, okay? It's going to be a less than or a greater than. And it unites with the boundary, and what do you expect the mathematics in the boundary to have? Equal sign, equal sign, equal sign, equal sign, equal sign, okay? So it's the combination of that. So if we were to look at this solid, what would we expect? What would we expect the math to actually be? Well, for the X surface, it is minus 3.5 less than or equal to X, less than or equal to 3. And so we've got two planes bounding this thing. We've got, on the Y, we've got two planes, 0 less than Y less than 6, less than or equal to 6. And then what is the surface for Z? Well, it starts at the 0 plane, but it goes up to this surface that is our Bezier surface, or our B-spline surface, or our NURB surface, goes up to that definition. Okay. So in the CAD system, it is running a set of equations where it's saying less than or equal to, less than or equal to, less than or equal to. And it's running, in some respects, a bunch of half-space calculations. So one half-space calculation, I've got to be left of this x-plane. I've got to be right of this x-plane. I've got to be right of this y-plane, left of this y-plane. I've got to be above this z-plane, below this z-surface. And so it's doing half-space calculations, but we don't think of it in terms of half spaces. But at the lowest mathematical level, that's exactly what it is. It's very quickly asking, am I left of this, right of this, above this, below this? One thing that I was going to mention before we started lecture, and this just reminded me of it. This MBE that's sitting here, okay? If this were a bicubic, cubic in U, cubic in V, if it were bicubic, we know what those things look like, the MBE or the MBE transpose. It's 1 minus 3, 3 minus 1. It's that stuff that we've dealt with over and over again. That is for the Bezier, right? What if it were a bicubic B-spline? Not Bezier, but a bicubic B-spline defined by the same control net. What would MB or MB transpose, what would that look like? Would it be 1 minus 3, 3 minus 1? In other words, are the coefficients to the blending functions the same for cubic Bezier, cubic B-spline, cubic nerve? Are they the same? Cubic Gordon's patch, cubic any other kind of surface, are they the same? Answer is no, they are not. Okay. Everything else is the same. The U is the same, the V is the same, the points are the same points, it's a control net of points, but it's a different blending function. So if you are reading along and all of a sudden you see a different set of 16 numbers and it's in a blending matrix and it's not the 1 minus 3, 3 minus 1 set that we've gone over, what can you conclude?
It's not a Bezier.
It's not a Bezier. You don't know whether it's a B-spline, you don't know whether it's a nerve, but you can conclude this is not a Bezier. Now, if you go on the internet, and you may want to just, not before the exam, it's not on the exam. If you go on the internet and you just say, show me a cubic B-spline, show me the blending matrix for a cubic B-spline, you would see a different group of 16 numbers, coefficients, for the B-spline blending function. It's got a bunch of zeros, which you would expect, but it also has a bunch of different numbers in it. Okay? Does that help you, hopefully? The mathematics of these curves are all the same, treated the same, act the same, behave the same.